So now we are ready to compare the variables motion between the rotational and translational motion. Okay, these are the kinematic equations that we learned in chapter 2. For linear motion, final velocity equals initial velocity plus at. For rotational motion, final angular velocity equals initial angular velocity plus alpha t. So one-to-one correspondence. We are replacing v by omega and a by alpha. The second kinematic equation that we learned in chapter 2, delta x is v initial t plus half at squared. So here, instead of delta x, you have delta theta for the angular displacement. It is equal to omega initial t plus half alpha t squared. Then the third kinematic equations, final velocity squared equals initial velocity squared plus 2a delta x for linear motion. For rotational motion, it becomes omega squared equals omega initial squared plus 2 alpha delta theta. So keep this in mind. All what we need to do is just to replace the variables of motion, to replace the variables of motions for linear or translational motion by the corresponding one for angular or rotational motion. As simple as that. We move on to learn about another variable, which is the tangential velocity and the acceleration. So here, if you examine this rigid body, it is in rotational motion. Any rotational motion will have a center, will have an axis, and the rotation happens around that center. So this rigid object is rotating around this center, around the origin. If you consider a point like this point P, it will have this trajectory during the rotation. R is fixed for this point. Each other point will have its own radius. But for this point, for example, this would be the radius. And we start here with theta 0 along the x-axis. So when this particle is in motion, when it reaches this location, now you have this angular displacement delta theta, and you have the change in arc delta s. So as we defined the angular displacement earlier, delta theta is equal to delta s divided by r. Now look what happened when we divide by delta t. Delta theta divided by delta t, this is just omega, the angular velocity. And the right side, delta s divided by delta t, this is v. This is v, the tangential velocity. Okay, so we have a new important equation that allows us to calculate the tangential velocity from the angular velocity. All what we need to do is just multiply the angular velocity by r. Multiply the angular velocity by r. So different points on this rigid body will have different values for r, right? Like if you take a point here, r will be less than r for this point. So from this equation, we understand that all points on the rigid object will share the value of omega, but they will have different values of r. Different values of r. Therefore, the tangential velocity will be different for different points depending on how far they are from the axis of rotation, while the angular velocity will be the same for all points on the rigid object. Okay? So we are dealing with angular velocity and tangential velocity. omega equals V over R, or V equals omega multiplied by R. Now to the acceleration. If you take delta V, it is equal to R delta omega. From this equation, V equals R omega. The change in V is equal to R multiplied by the change in omega, because R is constant. For the same point, R is constant. But when omega changes, V changes. Okay? So now, if we divide by T as we did before, delta V divided by delta T, this is the tangential acceleration. The acceleration along the tangent direction. And delta omega by delta T is alpha, the angular acceleration. So we have this nice relation that relates the tangential acceleration to the angular acceleration. Again, tangential acceleration is equal to the distance from the axis of rotation, R, multiplied by the angular acceleration, alpha.